Buddy, we are live with some more office hours with Chegg. This is the third time we've been doing this. I'm coming with you, come to you live every Tuesday, 5 p.m. Pacific time, to go over Organic Chemistry 1 practice problems. And this is the point of this is a live office hour. So I will be taking questions from the live chat. If you have any questions about some of the problems that I'm going over, feel free to ask. And if you have related questions too, that's the point. I'm here to take all of your questions. Please keep them Organic Chemistry 1 related. That's the purpose of these. You can see a QR code up on the top left if you want to check out Chegg's website and their channel. They have a list of the different kinds of office hours that are going to be going on, so that you can get help with all kinds of other subjects. If you're tuning in now, I do want to apologize for my voice. I was very, very sick for a few days, and I'm much better now, but I was coughing a lot, and my voice just got completely shot. So I've been drinking tea with honey all day, and it's actually quite a bit better. You should have heard me yesterday or this morning. But so we're going to go ahead and go through some questions. So today, what I wanted to do, the first session, we were focusing a lot on nomenclature. The second session, we were focusing a lot on isomerism. And so today we're going to review a couple of topics from the first 2 weeks, and then we're going to dive into the mechanisms. So I know that SN1, SN2, E1, E2 is probably the first major roadblock when people are studying organic chemistry for the first time. So we're going to tackle those. So once again, I apologize again for my voice, drinking the tea. And we're going to get through this. Okay. So let's begin. Now, week 1, we were looking a lot at nomenclature, and we did some IUPAC nomenclature of haloalkanes. We did some cycloalkanes. We didn't really do alkenes and alkynes. So let's take a look at some alkynes, and we're going to do some IUPAC nomenclature for these guys. So let's see here. We have got some alkynes. Now, if we have a triple bond on an organic molecule, the first step we have to do is we have to number the parent chain, and we are going to number the parent chain so as to give the triple bond occurring soonest. And that is specifically the triple bond because that takes priority over any halogen or alkyl substituent. So the way the priority goes is that the halogen and alkyl substituents are equal priority, and they are last. If you have a double or triple bond, those take priority over halogen and alkyl. Then actually a hydroxyl takes priority even over any double or triple bonds. So we're going to number this parent chain so as to give the triple bond occurring soonest, and that will be from this direction. So 1, 2, 3, 4, 5. Now, some students get a little confused with the triple bonds. These are carbons, right? The reason that it's linear like this is that sp hybridized carbons they exhibit linear molecular geometry, right? You've got a carbon that's triply bound to another carbon and then singly bound to another carbon. So it's got sp hybridized orbitals. That makes it linear. So these are actually separate carbons. So 1, 2, 3, 4, 5, and they have to be numbered that way because we want the triple bond occurring soonest. Now, once we have that, what are our substituents? We have a methyl, and a chloro. Now, which one of those comes first alphabetically? It's C for chloro before M for methyl. So we're going to call this 5-chloro. Now we've got the methyls, and we have to list both of them. They're both on carbon 4, but we have to say 4, 4 to make it clear that they're both on carbon 4. So 4,4-dimethyl. And then we have to specify where the triple bond is occurring. We have a pentyne, but the triple bond begins on carbon 2. So we have to say 2-pentyne, okay? So 5-chloro, 4,4-dimethyl, 2-pentyne, because C for chloro, then M for methyl, and then pentyne specifying where the triple bond begins. So that will be that one. Now let's do the same thing over here. we have got this triple bond here. Which way are we going to number the parent chain so as to give the triple bond occurring soonest? That would be 1, 2, 3, 4 from this angle, or 1, 2, 3, 4, 5 if we start from the right. So clearly we're going to start from the left, as that will get that occurring sooner. 5, 6, 7, 8, 9. So we certainly have a nonine. Okay. Now, what are the substituents? We have a methyl over here. We have a methyl over here. We have a bromo over here. Okay. So what comes first alphabetically? Bromo. So let's call this 8 bromo. And then we have two methyl groups. That's going to be 3, 7 dimethyl. And then the triple bond begins on carbon 4. So this is 4 nonine. Non for 9 carbons, ine for the triple bond, 4 because it begins on carbon 4. So that's a little bit of review of IUPAC nomenclature for alkynes. That should be pretty straightforward. Let me just make sure I caught any questions. Let's see. Atomic radius that's more gen chem, so maybe later. This person asks, hi, someone with bad foundation here in chem, trying to catch up before the start of my uni biomed course in 2 weeks. What is your advice to cover everything I need to know? So if you're doing biomedical stuff, you definitely, or organic chemistry is going to be key. So it's a ladder though. There's a lot of gen chem concepts that are very important for organic chemistry, like hybridization and acid base and all that kind of stuff. And then there's all the organic stuff. So just off the top of my head, definitely I have tutorials on all those topics for my general chemistry and organic chemistry playlists. Okay, guys, we can keep it topic specific here. A lot of people have some different questions. Okay. Victorious asks, any IUPAC nomenclature examples would be great. Specifically, do IUPAC rules break down at a certain point and we just have compounds that are unnameable? So no, certainly the whole point of IUPAC nomenclature is to be able to unambiguously name any organic molecule. So there would not be an example of any organic molecule that is unnameable, because there are specifically rules to be able to name any molecule. So that would be the case. VMB asks, can you explain enantiomers in the context of organic chemistry? Absolutely. I actually included 2 questions that were rollover from last time when we were talking about isomerism. So when I look at those are questions 3 and 4. We will talk about enantiomers there. Okay. Oh, very important question. Shwari, yes, asks, is it 4-nonine or non-4-ine? These are completely equivalent. They're both absolutely valid. I have a preference for 4-nonine. It's an aesthetic preference. That's just how I like to do it. But this is 100% correct. If you want to put non-4-ine, that is absolutely valid by IUPAC nomenclature. Excellent question. Let's see. Okay. History lover asks, can you explain ionization energy and electron affinity to me if possible? Those are general chemistry topics, so we probably won't cover those in the organic chemistry office hours, but feel free to email me. It's possible that we can get to that. Okay. If you're just tuning in, I apologize again for my voice. I'm drinking tea. My voice was much worse this morning, if you can imagine. Kilua Lusty asks, can you tell us the priority order for functional groups when it comes to naming compounds using IUPAC? So as I said earlier, the main ones that you want to remember are that alkyl and halogen are equivalent and they are the lowest priority. Then it's actually triple bond and then double bond. So actually a double bond takes priority over triple bond, strangely enough. I'm not sure why that is. And then hydroxyl takes priority over double and triple bond, and alkyl and halogen. There's obviously you can talk about priority for any other, right? You can like amino groups and things like that. It's not really that necessary to memorize, but yeah, that would be it. Evan asks, can you talk about reactions with Lewis acids and bases and drawing arrows? So that let's move on to number 2, because acid-base chemistry is extremely important in organic chemistry, and so we certainly have to know the definitions of Lewis acids and bases and Bronsted-Lowry acids and bases. So this says, which species can act as a Lewis acid but not a Bronsted-Lowry acid? So what are these, right? A Lewis acid will donate electron pair, right? Sorry, no, that's not right. A Lewis acid will accept an electron pair, and a Bronsted-Lowry acid will donate a proton. Okay, so the Lewis definition is about electron density. A Lewis acid accepts electron density from a Lewis base, which donates the electron density. A Bronsted-Lowry acid donates a proton. A Bronsted-Lowry base accepts a proton. So which of these can act as a Lewis acid, but not a Bronsted-Lowry acid? So what about water? What can water do? So water certainly can act as a Bronsted-Lowry acid, right? It can act as a Bronsted-Lowry acid and become its conjugate base, right? It can donate a proton to become hydroxide. So that doesn't work. H3O plus also certainly can act as a, here, let's write that somewhere else. Hydronium ion can certainly act as a Bronsted-Lowry acid. It can become water, right? If hydronium donates a proton, then the electrons in the bond to the proton will neutralize the oxygen and we get water. So those certainly can do that. Acetic acid also certainly can do it, right? It will become the acetate ion. So the point here is that BF3 can act as a Lewis acid, right? A base can donate electron density, right? Boron can accept a fourth bond from something like a hydride or whatever it might be. And so that can accept electron density, but it cannot donate a proton because there is no proton, right? There are no hydrogen atoms. So if something does not have any hydrogen atoms, it cannot be a Bronsted-Lowry acid because it has no protons to donate, right? So that would be the answer there. Okay, let's check if I missed anything. John asks, in what ways does the concept of resonance challenge the idea of a single true molecular structure, and how does this impact our understanding of reactivity, stability, and chemical behavior? That's a very good question. So with resonance, the key thing that we have to understand in organic chemistry is that we frequently draw individual resonance structures in order to write out mechanisms and things like that. But it is the case that individual resonance structures do not exist. The thing that exists is the composite resonance structure. So, like for example, if you have nitrate, and we did this last time. If you have NO3, right? This actually does not exist. Wait, no, sorry, that's not what I meant. Yeah, this. So this actually does not exist. Instead, it is a composite with electron density, pi electron density all around the molecule. So pi electron density can be delocalized, and if you take the composite of all the individual resonance structures, that gives you the composite, and that is the structure that actually exists. Let's see. Okay. Um, So there was a TikTok question from Yusuf about oxymercuration, demercuration, and anti-Markovnikov reaction. I will probably, excuse me, I will probably start on the addition reactions next week. Today, I want to focus on SN1, SN2, E1, E2. But then I will throw in a lot of the addition reactions. That's usually the next block after the basic mechanisms. Megan asks, hey, can you please repeat why the first naming of alkyne is 2-pentyne at the end? So the parent molecule is a pentyne. So the last thing we're going to name is the parent molecule, the pentyne. So when you're naming a molecule, first you name all the substituents. You list your substituents in alphabetical order, and then you get the parent molecule. So the molecule is a pentyne. So we're going to list all of our substituents and then 2-pentyne. Right? That's how we do that. Okay. Kilua asks, can you please clear the waters as to why water can act as a Bronsted-Lowry base and acid, and why it would not be considered a Lewis acid? So again, a Lewis acid is something that accepts electron density. And so what could be considered on water to be a Lewis acid would be the proton, right? So if a base interacts with a proton and extracts that proton, the proton is acting as the Lewis acid. So in a sense, water is acting as a Lewis acid, but it's really that proton, because then the electrons from that bond are staying with oxygen. So they're just different definitions, right? It doesn't mean something can't be both, right? When something is acting as a base and getting a proton, it is really acting as both a Lewis base and a Bronsted-Lowry base. There's really no difference there. The key is really the definition with acidity, because there are things that have no hydrogen content that are acids. That's where the Lewis definition comes into play. Okay, let's see. Oh, John asks about favoring substitution over elimination. Thank you for asking that. And I have a question coming up very soon that will answer that. So let's sit tight for that. Okay, we're all caught up now. So just to quickly review some of the stereoisomerism, draw an example of a meso compound. So this would be an example of a meso compound. A meso compound is one where we have more than one chiral center, but the molecule is achiral overall because of an internal plane of symmetry. So here we have two chiral centers. The carbons that bear the bromine, the bromo groups, are chiral centers, but there is an internal plane of symmetry here, right? If we take the mirror image, we just get that molecule. So that is achiral, meaning this particular stereoisomer does not have an enantiomer. So earlier someone asked about enantiomers. So, but here would be a diastereomer. So this can have stereoisomers, and not all the stereoisomers are chiral. So here would be a diastereomer of this first one, and this is chiral, right? This is achiral because it's meso, right? But this is a different stereoisomer of that, and it is a chiral stereoisomer. And this also has an enantiomer. So the enantiomer is just the mirror image, and that will be with the dash bond over there and the wedge bond on this side. So these are actually different molecules. So, if a molecule has n chiral centers, that molecule, there are 2 to the n possible stereoisomers for that structural connectivity. And all of those stereoisomers may or may not be chiral, right? They could all be chiral, but some could be achiral if there's a plane of symmetry. And that is this right here. So this is an example of a meso compound. Parth asked, what is an isomer? So isomers are different structures. So there's different kinds of isomers. A structural isomer would be 2 molecules that have the same formula, the same molecular formula, but differ in the way that they're connected, in their connectivity. A stereoisomer are molecules that have the same molecular formula and the same structure, but they differ in the way that the atoms are oriented in three-dimensional space. So these are stereoisomers of one another because on one, both the bromines are cis, and on another, the bromines are trans to each other. So those would be stereoisomers. Andrew says inverting both chiral centers will just make the same molecule its mirror image, but if it's its mirror image, it's not the same molecule, right? Mirror images, the mirror image of a chiral molecule is not the same molecule. It's enantiomer, a different stereoisomer. So that's a very important point to understand. Let's see. Okay. Yep. Okay. So now let's do an example of a molecule with an inversion center. So this is a different kind of internal symmetry that can render a molecule achiral. So for example, let's say we have this situation, and let's say we have F right there, F right there, Br right there, Br right there, Cl right there, Cl right there. So instead of an internal plane of symmetry, an inversion point or an inversion center is a point of symmetry. So if you reflect every atom across the central point of this molecule, it will see itself. So fluorine sees itself right there. Bromine is coming towards us, so it travels backwards through the center of the molecule and then farther backwards to hit the other bromine on the dash, which is farther away from us than the screen. The chlorine is farther away from us than the screen, and then it travels towards the plane of the screen and then beyond, even more towards us, to the chlorine on the wedge bond. So every atom, and then obviously the carbon sees itself across the carbon-carbon bond. So every atom sees itself across the inversion center, and so that makes this achiral overall. Whoops. What's happening? Okay. That makes this achiral overall because of the inversion center. So if, again, someone asked earlier about enantiomers, if something is achiral, then it doesn't have an enantiomer. It has to be chiral in order to have an enantiomer. If it is achiral, it will be the same as its mirror image, which means it does not have an enantiomer. If you're just tuning in again, sorry, I apologize for my voice. I'm drinking tea. I'm actually a lot better now, but my voice became quite shot. Now I'll turn the light on because it has gotten quite dark here. Okay. Now, let me see if I missed any questions. Okay. Let's move on. So now I want to talk about the mechanisms. Sorry about that. Okay. So SN1, SN2, E1, E2 are definitely, this is a first really big stumbling block for a lot of students. So here, this is a very, very simple and very straightforward SN2 reaction. So CN minus is a classic SN2 nucleophile. Remember, nucleophile is something that is electron rich, and then an electrophile is electron poor. So with all these mechanisms, and really every reaction in chemistry almost, we're talking about electron rich meets electron poor. We have some excess electron density is meeting some electron deficiency, and there will be a reaction, plus and minus attract, right? So we have Cn minus, that's your classic SN2 nucleophile, and we have this carbon here that is attached to the halogen. Carbons that are attached to halogens are classic sites of attack for SN2 nucleophiles if they are primary or secondary carbons. So let's have this attack right here. So this is how electron pushing arrows go. If this is your first exposure to electron pushing arrows always go from electron rich to electron poor. So starting with a negative charge or a lone pair, and they're going to go over here, and then that is going to kick off this leaving group here. So what do we end up with? We have that phenyl, boom, 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 boom. And now the thing that we really need to understand is that SN2 will occur with inversion of chirality. So the reason for this is that in order for a nucleophile to attack, it has to dump electrons in the lowest unoccupied molecular orbital of the atom that it is attacking, and the lowest unoccupied molecular orbital for that carbon happens to be an antibonding orbital that is located oriented 180 degrees from the carbon leaving group bond. So here's the carbon and the leaving group. The orbital that the nucleophile needs to dump electron density into is 180 away from that. So it's going to do what's called a backside attack. It's attacking from the exactly the opposite side of that bond to the leaving group. And so because of that, whatever the stereochemistry was on the starting material, that is going to be inverted on the product. So usually when we're doing these, it's pretty easy. We have this on a dash bond, so the new group is on the wedge bond. If it was on the wedge bond, your answer is going to be on the dash bond. It's usually pretty straightforward like that. So this is SN2. This is your straightforward SN2 reaction. It's very easy. Okay, let's see if I missed anything. Jack on TikTok, where the 1-2 shift. Yes, that is actually on here. I will get to a carbocation rearrangement on here. Doctor, yes, I apologize. I am sick. I'm actually much better now, but I was really bad yesterday. I don't know what that means. Oh, this is great. John asks about rate determining step and leaving group ability. So we're going to look at some energy diagrams right here. It's carbocation stability is definitely the main factor. Let's see. Oh, this is an excellent question. So Mark Yannick asks, is that carbon very electron poor since iodine's electronegativity negativity is nearly equal to carbon's? That's a great point. So it is true. Usually, if we have something like a carbon-chlorine bond, that is quite a polar bond because of the discrepancy electronegativity. So here it's a carbon-iodine bond. It's not so much the difference in electronegativity, but what happens is because iodine is so large that bond, the electron density in that bond becomes extremely polarizable. And so if a nucleophile approaches, it is the fact that that concentrated negative charge is approaching that portion of the molecule. It will cause the electron density in that bond to polarize as a result of the electron density approaching. And so it's almost like an enhanced momentary dipole. So that's actually what drives the leaving group ability of the iodide there. That's a great question and a common question because it's true. Just looking at electronegativity values, you wouldn't know, but it's the polarizability of that group. Okay. Yes, SN, yeah, carbocation formation is the rate determining step. We will look at that right now. Can you move the title so we can see the full screen? Shwari asks, why does CN minus favor SN2 as opposed to another mechanism? So it's just that it is so it's bullet shaped. C triple bond N is totally linear and very bullet shaped. So there's not a lot of there's not a high activation energy associated with it approaching the molecule and coordinated. It's also a highly localized charge. The more localized charge is, the more likely it is to coordinate. So that's why those two reasons combined are why CN minus. Anytime you see NaCN, KCN, right? We know that, first of all, we have to know that it's ionic, right? So if it just said KCN, we do have to know that that means K plus Cn minus, right? Here it's listed as Cn minus in the counter ion, but you do need to know that. And then we need to know that Cn minus is a classic SN2 nucleophile. Okay. Got it. All right. So we had some talk about mechanisms and stability. So match the energy diagrams with the statements describing them. So we have a few different, so these are representing some mechanisms, some pathways. So first, we want to know about reactions proceeding via an intermediate. So remember, any reaction is going to have an activation energy, and then it's so there's reactants, an activation energy up to a transition state, and then it'll go down to products. So reactants and products, one will sit higher than the other depending on whether it's endothermic or exothermic, or in this case exergonic or endergonic, depending on if we're talking about enthalpy or Gibbs free energy. But so if there is truly an intermediate, so remember, a transition state is not an intermediate. A transition state is an orientation that is reached for an infinitesimal moment on the way to products. An intermediate is a truly isolatable structure. So there has to be a dip down. There's a little stable valley. That is an intermediate. So this is an intermediate, and this is an intermediate, right? We have an activation energy in the transition state to get to this little valley, the intermediate, and then a second reaction. Here we have one reaction to the intermediate and then a second reaction, right? So that means that A and C are reactions proceeding via an intermediate. Now, possible diagram for an SN1 reaction. So with the SN1 reaction, an SN1 is a two-step reaction. So people sometimes find that a little funny, that SN1 is two steps and SN2 is one step, but the number there is referring to the transition state. The SN2 has a bimolecular transition state where the nucleophile and the leaving group are both weakly coordinated to the substrate at the same time. So two things are coordinated SN2. SN1, there's two discrete steps. First, the leaving group leaves. You have the unstable carbocation intermediate. Then the nucleophile coordinates. Two different steps. Each will have its own activation energy, and the carbocation formation is the rate determining step. That one is the more energetically unfavorable step. So if we want to find an energy diagram for an SN1 reaction, we know that it has to have two steps, it has to have an intermediate, and the intermediate must be much higher in energy than the reactant. So the activation energy of the first step has to be much greater than the activation energy of the second step. The activation energy of the second step is very low, right? It just coordinates. The nucleophile coordinates and neutralizes the carbocation, very energetically favorable. So we have two here with an intermediate. Which of these is the one that has a very energetically unfavorable first step? That's the rate determining step. So it's clearly going to be C, right? We start here, and then we have a very large activation energy to get to the intermediate. Then once we're at the intermediate, there's a minuscule activation energy, almost none at all, to get to a more energetically favorable product. So certainly C would be the energy diagram that would make sense for an SN1 reaction. Okay, which of these would be the fastest reaction? So when we're talking about kinetics, we're looking at activation energy. So thermodynamics has to do with delta H or delta G. That would be the distance from reactants to products on the energy diagram. If we're talking about rate, we're talking about kinetics, we're talking about the activation energy, because the activation energy is the energy with which the collision must occur in order for the reaction to proceed. And if the activation energy is very, very high, that means that only a small proportion of the collisions will have enough energy to get over the reaction barrier and go to products. So let's say the activation barrier is very high, and that's such that only 1 in 100 collisions has enough energy for the reaction to occur. That means it's going to have to react for a very, very long time, because only 1 in 100 collisions will promote the reaction occurring. But if the activation energy is very, very low, that means that most of the collisions, or many, right, proportionately many more collisions, will promote the reaction occurring. So if the activation energy is low enough that 7 out of 10 collisions result in the reaction occurring, then it's going to go very fast, because almost every time a collision occurs, you'll get the product. So if it says the fastest reaction, what it's really asking is which has the smallest activation energy. And the activation energy is the distance from reactants to transition state. So we look right here for D. Here is the reactants, and here is the transition state. This is a teeny tiny little activation energy, right? It's a tiny little bump. Imagine how little energy it would have to be, you'd have to provide to roll a ball over that hump. You can just roll it very lightly, and it'll go over the hump and go down. Whereas this is a huge activation energy over here. This is a very slow reaction, because think how much energy you have to use to roll the ball up there, right? It's going to take forever to so much energy to roll the ball up there. So that will be a very slow reaction. This one will be very fast. D is the fastest reaction. Apologies again. I'm still getting over this cold. Now, this asks which is the reaction with only one transition state. So every reaction has a transition state. Every reaction has reactants and products. It has an activation energy to get the transition state, and that's true for any reaction. So if there is only one transition state, that means there's only one step. So that would be B and D here, right? These guys have two transition states. Transition state 1, transition state 2. Transition state 1, transition state 2. These guys have one transition state, the top of the hill. That is the transition state. Okay, let's see if I missed anything. My last name asks, how can we determine between SN1 and SN2? Excellent question, and we're going to get to that because that's a classic question that everybody always asks. Nat asks, are these weekly? Yes, these are weekly. I will be doing Organic Chemistry 1 review with taking questions every Tuesday at 5 p.m. Pacific. Let's see. Okay. Okay, 7. So this question was asked earlier. Why do hot temperatures favor elimination over substitution? So let's take a look at, let's say we have a leaving group here and a nucleophile attacks, and we go like this, and we get, so that would be SN2, right? Now, instead, let's say we have a leaving group and we have some base, and we have a proton there, and we get the proton, and then this goes here and kicks that off, and we get the alkene product. So why would a hot temperature favor elimination over substitution? So this is the important equation, the Gibbs free energy equation. So this is delta G is change in Gibbs free energy. It determines the spontaneity of a reaction. So if delta G is negative, it is spontaneous or exergonic. If delta G is positive, it is non-spontaneous or endergonic. Delta H is enthalpy, which is basically change in energy if it were at constant pressure. So it's exothermic if it is negative and releasing energy. It is positive. It is if it is positive, it is endothermic, it is absorbing energy. T is the temperature, Kelvin, and delta S is change in entropy. Change in entropy is measuring the dispersal of matter and energy in the system. Now, what can we say about the change in entropy for these? Here we have two things going to two things. Because, sorry, let me include, right. So for a substitution reaction, we have a nucleophile attacking a substrate, and then we have the new product and the leaving group that left. So we started with two things, and we end up with two things. Over here, we have a base, and we have the substrate, but then we have BH plus and LG. After the elimination, we have the alkene product, we have the conjugate acid of the base that's now been protonated, and we have the leaving group. So we're going from two things to three things. That is an increase in the dispersal of matter, which means it is entropically favorable, which means we have a positive delta S. This is entropically neutral, right? This is not really entropically driven. An elimination is entropically driven. So if we have a positive delta S in our Gibbs free energy equation, the higher temperature is, the bigger this term becomes, right? If we get hotter and hotter and hotter, the entropic favorability term becomes more and more significant, and the more likely that delta G becomes negative or more negative, right? So imagine we have delta H, and then we have this term. The bigger the second term becomes, the more likely that delta G becomes negative. So entropic favorability is enhanced at high temperatures in the context of determining whether a reaction is spontaneous or not. So if in terms of favorability, we're basically saying what's going to happen, what's spontaneously going to happen. If it's entropically favorable, heat it up, it's more likely to occur. So that is why when you're looking at what might happen and you're unsure of whether substitution or elimination will occur, take a look at the temperature. The hotter it is, the more likely that elimination products are going to dominate in the product mixture. So that's a very important concept. Let's see if I missed anything. Thank you for saying hope you get well soon. I'm actually much better today, but the coughing really shot my voice. I do apologize about that. Okay. Number 8. Draw the product of the following reaction. So a few things to talk about here. So we know that, when you're talking about SN1, SN2, E1, E2, sometimes we can make a little chart. And the first thing we're going to do is we're going to look at the strength of the base. So first of all, we have to know that, for example, if you see something like this right here, this is shown to you to be ionic, right? But even if it's not explicitly written that way, you have to know that it's ionic. And the way that you know is if you have potassium or sodium, right? If you have a metal counter ion, you know it, right? Potassium or sodium, these are positively charged metal ions. We know that they're acting as counter ions to an anion, right? So we know that we have ethoxide. So even if it wasn't explicitly written, if we just see this or whatever other way, right? O, CH2, CH3, whatever it is, we know that we have an alkoxide ion. We have an ethoxide. That's a very strong base or nucleophile. If it's very strong, then we don't have to wait for a carbocation to form. So we know that SN1 and E1 are not going to happen because the base, the nucleophile, is going to react, right? It takes a long time for a carbocation to form. So if something is going to happen faster than that, we're not going to consider those mechanisms. Now, ethoxide there is some ambiguity here because it is possible that some SN2 could occur, but there's some beta branching. Ethoxide is of moderate steric hindrance, right? It is linear, so it's not extremely sterically hindered, but there is some steric hindrance there. There's beta branching. So we're probably going to say that E2 is going to be the case. So now the question with E2, it's very important when we have cyclic structures, if you have substituents that are adjacent to the carbon that's bearing the leaving group, you have to draw the chair to know what is going on. So let me draw the chair here. I could do that better. Okay. So here's the chair. I'm going to draw the bromine up. Now, if we go one clockwise, we have a methyl down. And then over here, we have an ethyl group up. So that means also we have a proton here and we have a proton here. Now, the reason that we have to draw this is that in order for elimination, in order for E2 to occur, both the proton being extracted by the base and the leaving group have to be axial because they have to be anti-paraplanar. The only way for the p orbital overlap to occur in order for the pi bond to form is for the leaving group and the proton to be axial and anti. So if we were to draw the Newman projection of this bond right here, this bromine and this proton would be anti to one another. So the reason that we had to do that is that only if we draw the chair, we can see that this proton is not available for elimination. If we did it over here, we might think, okay, look, we have some alpha protons. We have a proton over here. We have a proton over here. We have two protons available for elimination. Therefore, there are two isomers. There are two structurally isomeric products. But it's not the case because this proton is not available because it is not axial, right? We have to put the leaving group axial, and then the adjacent proton, the alpha proton, also has to be axial. So it is only this one that is available. We have to get that one. So what we're going to do is we're going to say here's ethoxide. Ethoxide is going to go over here and get this proton. These electrons will go to form a pi bond there, and then the leaving group will leave. And I'll draw that over here too, just to be clear. We're going to get this proton. We'll get the pi bond there, and then this will leave. So we will get the ethyl group there, and then this methyl group will still be on the dash bond because no chemistry has occurred here. So once again, we had to draw the chair because the leaving group and the proton being extracted must be anti-paraplanar. And the only way for them to be anti-paraplanar is for them to both be axial. So we had to draw the chair with the leaving group axial, right? We could have drawn the chair with the bromine equatorial, but that's not the chair from which E2 will occur. We have to then flip it and draw the one where the bromo is axial. And then we see, do we have any alpha protons that are also axial? And it turned out that one of them was not. This one is. And so we can get that one. So then going back to this top-down notation, we're ethoxide will grab that proton. We'll get the double bond here. We'll kick that off. And so that is going to be our product. And that is an E2 elimination. So that's that one. Okay, let's look at a similar one here. Draw the product of the following reaction. So again, the exact same logic is going to apply. SN1, SN2, E1, E2. We have tert butoxide. Tert butoxide is a very strong base. Any alkoxide is a very strong base. So that's really the first thing that you want to look at is the base or nucleophile and look at its strength. It's very strong, and so we're not going to have to wait for SN1 or E1. We're not going to wait for carbocation. It's going to react. It's either going to extract the proton or it's going to coordinate. Once we've done that, now let's look at sterics. What is the sterics of the right? Could it do SN2? Well, according to the substrate, it could. It's secondary. There's beta branching, but not too much. So if it was a hydroxide, maybe it could do it. But we have tert butoxide. Tert butoxide it's the quintessential, it's the classic E2 base because it's so strong that it's going to do SN2 or E2, but it's so bulky that there's too much activation energy. The activation energy associated with this bulky base approaching the molecule and coordinating is too high. It's not going to be able to coordinate. It's going to do E2, right? So no SN2 because of the sterics associated with the base. So, but remember what we just learned about. We have to draw the chair because it may not be the case that all of the protons that seem to be available for elimination are indeed available. So I like to just put the bromine axial right there, right? We have bromine up right there, so that's fine. And then if we go counterclockwise 1, we've got a methyl there, and then we have hydrogen there, which means on this side we have 2 hydrogens. So in this case, we do have 2 protons that are available for elimination. Boom, boom. We have 2 alpha protons that are axial. So each of those is paraplanar, antiparaplanar to the bromine. And so either of them can be extracted for E2 elimination. But this is where the sterics on the base is very important. Because it is so bulky, the activation energy associated with approaching the less substituted carbon is so much lower that it's going to actually prefer to go that way. So here we have, this is a tertiary carbon, and this is a secondary carbon. And so it's actually going to approach over there, right? So let's draw a hydrogen here. What's going to happen is it is going, because of the sterics of the base, it is going to attack at that location and then make the pi bond there and kick that off that way. So if we're looking at it from over here, it's going to get this proton. These electrons in that carbon hydrogen bond will form the pi bond, and then these electrons will leave with the leaving group. And so this is going to end up looking like this. We have the pi bond there, and then we have the methyl group still there, and it is still on the wedge bond because no chemistry has occurred there. Remember, if you have an sp3 carbon, right, we're not going to flatten that out. These 2 carbons are now sp2 carbons. So there, right, we have implied hydrogens here. Those are flat, right? That portion of the molecule is flat, and they're implied, so we don't need to draw them. But this is still sp3, so that has to have a wedge bond there. And this is called Hofmann elimination because we got the less substituted alkene product. If we had hydroxide and it was hot, so that it could have been SN2 or E2, but the heat would make us go E2, then we would have gotten probably the Zaitsev product, right? Because if it was right, if we had OH, we would go to that one. If we had OH, so that's so sterically unhindered that it has equal access to any of the protons. There's not much of a difference in the activation barrier between hydroxide approaching this proton or that proton. So we would go and get the one that would produce the most stable product. This product sits lower on an energy diagram than this product. The Zaitsev product is the thermodynamically favored product because it sits the lowest on an energy diagram because it's the most highly substituted alkene. This alkene is tri-substituted, right? Carbon, carbon, carbon. This one is only di-substituted, the 2 carbon directions in the ring. So this sits higher on an energy diagram, but this will be the Hofmann product is preferred because this is kinetically driven, right? Because of the bulk, the sterics associated with the base, it's going to go via the smallest activation barrier. So the Hofmann product is kinetically driven. The Zaitsev product is thermodynamically driven, sits lower on the energy diagram. So that's a very, very, very important concept to understand. The thermodynamically driven product versus kinetically driven product, which has application in many different kinds of reactions. Here it is applied to 2 possible E2 reactions. Okay, so let me just make sure I didn't miss any questions. I think we had a lot. Okay, let me go from there. Schwari says temperature just didn't come up. The only conditions we were taught to consider were the qualities of the solvent, base, nucleophile strength, and sterics. So, well, temperature is very important. I mean, it is going to hotter temperatures will favor elimination over substitution. Colder temperatures will favor substitution over elimination. Type of solvent is also important. Just to give you one thing about solvent, if it is protic or aprotic, that can affect like nucleophile strength. Like, for example, the halide ions are good SN2 nucleophiles, but the fluoride ion would be the best SN2 nucleophile in an aprotic solvent. But if it's protic, then all of a sudden it's coordinating with protons from the solvent, which it acts up. It actually ends up reversing the trend of nucleophilicity. So the halide ions, F minus is the best, I minus is the worst in aprotic. But if it's protic, it reverses, and I minus is the best, and F minus is the worst, because I minus is not at all basic because HI is so acidic. So it's not interacting with protons, which means it is still very able to act as a nucleophile. So that's just one example. Let's see. Binka asks, what is your favorite part about organic chemistry? I just think it's really cool that we figured out, first of all, the structure of all molecules, and then can build any molecule we want. I think that's incredible. Okay, that's it. Let's see. I think we'd have just maybe 1 minute or so. So I think let's keep it there. I will go ahead and roll over. I have about 3 more that I will roll over to next week. So, excuse me. So SN1, SN2, E1, E2 are extremely important. That's where Organic Chemistry 1 students first begin to learn about mechanisms. Electron pushing arrows. Electron pushing arrows will be important for all of the mechanisms you learn in organic chemistry. So this is where you sort of start familiarizing yourself with that. So I will continue to throw 2 or 3 questions, easy questions like this, in probably every week as we go, just for anybody who's tuning in and needs to review those basics. Next week, I also will start throwing in some addition reactions, because addition reactions are usually the next block after SN1, SN2, E1, E2. Although I got to be honest, every class is the same. That's how I taught it, and that's also how I was taught. But I have encountered people who have professors that do addition reactions before SN1, SN2, and all that, which to me is crazy. But some people do that. And so that will be the plan. So yes, once again, next week I will be much better. My voice will be much better, unless one of my kids gets me sick for the 3rd time in like 3 weeks, which could happen. But yeah, so we are here 5 p.m. Pacific time every Tuesday. Again, partnering with Chegg. And I'm bringing you office hours for Organic Chemistry 1 review. I'm trying my best to follow a typical semester pacing for students who are in ochem 1 right now. But go ahead and check the QR code on the top left and go to Chegg's channel and their website and see what other office hours they are offering. There may be other courses you are taking that they have office hours for those subjects too. So lots of great study time going on with Chegg these days. And so that'll be it for this week. So thanks to everybody for tuning in. Thanks for sticking more on topic this year with your questions. And tune in next week, same time, 5 p.m. Pacific, next Tuesday, and we'll do some more Organic Chemistry 1 review.